So let me just say hello and welcome to VeloVirtual. This is Velo3D's application deep dive webinar series. Today we're talking about a new topic, something we've never really gone down and talked about before, downhole drill bits. So really excited to be here today. This is a session that has everything. So I think you're going to really enjoy this one. This has topological optimization, advanced simulation, it has metal additive manufacturing, some of the smartest engineers that I've had a chance to talk to doing some amazing work, all combined together to make one great story. You know, we tend to talk about heat exchangers in metal additive. We talk about rocket propulsion aviation, but until now, we really haven't talked about parts for the oil and gas industry, specifically drilling. So this is going to be a really good one. In drilling, you know, we look at optimization. We look at the challenge of optimizing parts. And in this context, optimization means a higher rate of penetration of the rock substrate. It's also a longer lasting drill bit. So this is about reliability as well. And current designs, they're optimized for hydraulics, make no mistake about that, but they're also designed to be manufactured by conventional means. And in our experience, what this usually indicates is that there's potential left on the table. And when we see that, we get excited, right? So analyzing the results of modern topological optimization, CFD, designers at CDS found that room for improvement. And they have updated this design by updating their manufacturing technology. And they are leveraging the geometric freedoms created by advanced metal additive manufacturing, or you may also know this as metal 3D printing. So today we're joined by CDS, Ansys, and Velo3D engineers for a look at how that synergy of modern software, advanced manufacturing, can unlock these new capabilities for parts like downhole drill bits, estimated to be a $5 billion market by 2026. So really, really great opportunity here. Now, let me introduce our speakers today. It is an honor to have on our show Rushik Matroja. He's a mechanical engineer with 7 years of experience in additive manufacturing, mainly in Japan. He has worked on more than 100 different engineering projects regarding AM. He is a CATIA champion and one of the first people to introduce topology to Japan. Now, he is the CEO of Cognitive Design Systems, a startup creating innovative solutions to automate and accelerate your design workflows for additive manufacturing. Dr. Sunil Acharya is an engineering simulation expert with 21 years of industry experience in simulation-based techniques for product design and process modeling. As a lead application engineer for the Ansys Customer Excellence, or ACE team, Sunil's primary area of expertise is in materials and multi-physics modeling. Sunil is a mechanical engineer from IIT in Bombay with a PhD in polymer engineering and an MS in biomedical engineering from the University of Akron. Sunil is a member of NAFMES. I'm sure there's a better way to say that, but I'll let you pronounce it. Manufacturing Simulations Working Group and the Digital Twin Consortium.
It's NAFMS.
I knew there was a better way to say it. Thank you for that. Last but not least is Matt Kurish. He's a technical sales engineer at Velo3D. As a technical sales engineer, Matt specializes in helping companies get the most out of Velo3D capabilities for their in-part applications. So not how to use the printer, but actually how to use these printers to solve your engineering problems. He started his career in backup power generation before moving to commercial aviation. He's worked on high pressure turbine blade designs. He's worked specifically in additive manufacturing since 2017 and has experience in several disciplines, including laser, powder bed fusion, E-beam, binder jetting. His previous roles include companies like GE Aviation and Caterpillar. He is also a hell of an engineer and holds a BS in mechanical engineering from Georgia Tech. So Rushik, I will turn it over to you.
Thank you very much, Mike. It's a pleasure to be here, and thank you very much, everybody, for joining us. Today we are going to talk about a very special part called the PDC drill bit. PDC stands for polycrystalline diamond compact and the drill bits. It's used in the oil and gas industry in order for the soft medium to hard soil for the extraction of various gases or oils. And the part itself is already a very highly complex part. And it really makes sense to think about additive by looking at the part. But the part currently has been optimized for hydraulics for the conventional manufacturing processes. And today we are going to explore even further what are the current issues with this part, how it is, and how we can improve it. Just for a reminder, this part is a very expensive part, so it actually makes a lot of sense to think about going to additive. In order to do that, first of all, I will be doing multiple different optimization processes. First of all, we will do a CFD analysis, mechanical analysis, and with Ansys Fluent, in order to understand better like where the problem stands. After that, based on that information, we would go through topology optimization, and we will also optimize the path with regarding the CFD results. And at the end, we will combine all these different optimization results, create a single unit, and we will improve the manufacturability of the part by adding extra features, the rules of additive manufacturing, so DFAM rules, applying some lattice structures where it's required, and at the end we will go through a validation with some for the mechanical stresses. So first of all, to understand better, like what kind of loads are applied on this part itself. So as we can think that this small bits that you can see, these are the PDC, and that's where all the cutting is done. A lot of pressure is applied on that very small section of the part, and of course the motion of the turning also generates some kind of the load on the part. On top of that, we have an axial load, which is due to the whole drilling process, and the various different kind of loads are applied on the bottom surface at that part. And at the end, we have mud extraction pressure. So there is a jet, the water jet, which is pumped in, and we try to extract the mud from the side of the pot. This creates erosion. There are also a lot of other issues which comes with it, but there is also a lot of internal pressure in the pot itself. So we'll be trying to understand that. To run through, we did some CFD analysis. To do that, in order to do that, we set up our workflow on Ansys Fluent with the fluid domain. We also meshed in a way that it's properly meshed in a way to have the most accurate results, and we applied the various the flow related load cases. Some results regarding all this. So first of all, we have a static pressure, which is mainly, as we can see, it's inside of the pot. So it's where the water jet is, the pressured water is coming from. That part is highly stressed, and that's where we can believe that there can be some erosion could happen due to the highly pressured liquid going through it during the whole cutting process. We have we also measured the fluid velocity. So once the pressure is coming out, the mud extraction, the mud will be going upwards. The velocity of the fluid will change. And we our main focus here was to analyze the residence time of the fluid. High residence time caused the wear to the part. And at the end, the shear stress that we can imagine with the axial load that we have, which is also a cause of wear. The erosion rate in the part itself, when we analyzed it, we saw that there were some zones where the erosion was happening a lot. This is inside, so this is due to the water jet, the jet pressure, and the outside, the how can the red zones are due to the high residence time of the fluid. Based on these results, we decided to do topology optimization and fluid optimization. So we divided the whole problem into two separate problems. So first is the external loads, which are mainly mechanical loads. We applied it in the external of the part. We received this topology optimized result. This was done on topology. We also did some fluid optimization, so to have a better the fluid flow, the channels in a way that we have the least amount of pressure loss. In order to have that, we received this kind of path. We combined them together, and it created a very organic looking beautiful path. But after all, this is a drill. This needs to be it cannot have any kind of holes. So what we did is we applied a shell, and we applied instead of applying the shell inwards, we applied it outwards in a way that the topology optimization result is used as ribbing itself. This whole process created a very organic looking this part, which is highly complex inside, but even from outside we can see all kind of complexity. All this Boolean operations and creating of the shell was done on topology by using the implicit modeling. Based on the CFD result on the residence time of the fluid, we iterate some designs for the grooves, which we can see on the outside. The original grooves are very simple. It's made for the conventional manufacturing process. But instead of that, we improved the design in a way that the fluid flow and the groove designs follows each other perfectly. So this grooves were added on top of it in order to have this organic shape. And at the end, the part which was topology optimized and fluid optimized is looking very different. And this optimization was due to it was a manual optimization process. So we went through the CFD analysis on Ansys Fluent, and we extracted the results, some point maps of the at each position, each point in the mesh, where the what kind of velocity we have, and based on that result we changed the geometry in order to have this. We also wanted to reduce the weight of the part itself, because the current weight, if we want to manufacture it through additive manufacturing, it would be a kind of trouble, because that would create a lot of concentration of heat while manufacturing. So in order to reduce the weight and in order to reduce the risk of heat concentration, we applied lattice structures in the hollow parts that were remaining, and these lattice structures are cylindrical TPMS structures, which also improves the manufacturability as a whole. And we don't require any kind of supporting such structures for internal overhangs. Everything was covered thanks to this. once we have created this kind of internal cavities, we needed to evacuate the powder because we wanted to produce it with powder bed fusion technology. And in order to do that, we created the holes at the right position in the top of the pot here and the bottom, and in order to have a easily removable powder zones. At the end of that, we did some mechanical testing with the worst case scenario, and this part, first of all, this part was manufactured in Inconel. So the maximum Von stress that we obtain is way below the Inconel's yield strength, and we were satisfied with the result as a globe, in a whole. After that, we went through the manufacturing process analysis with also Ansys additive manufacturing suite, where we used the powder bed fusion technology and Inconel as the material itself to go through the manufacturing process itself. Here you can see that the part itself was printed in this direction, and we can see in the yellow we have the support structures, and the part was printed like this. Velo3D will be talking more about more in detail about how they printed the part. But the simulation of the manufacturing was done first to understand the displacement that could occur during the manufacturing process. We had we had the result. We knew where there is a risk zone. We also had the Von Mises stresses during the manufacturing process, and here is the result for it. There is also one analysis about the blade crash. So we believe that as we are using powder bed fusion technology, there will be a recoater blade putting the powder, laying it down. And what is the risk to it? As we can see here, that this part itself has a lot of zones where there is a risk for the blade crash. So these are all the concerns that we had before the manufacturing even was done, and we were aware of the issues, and that's where we contacted Velo3D and asked for their help, and I pass it over to them.
Thanks, Rashik. So where does Velo3D come into play? They do all of this high-end analysis, come up with this beautiful design, and then do their build prediction and have some concerns about things like recoder interaction. So just looking at the part itself from a high level and where the design stands, the way and what they came up with, they've got a lot of complex, both internal and external features with lightweighting lattice, geometries, contours, and things like that would be very difficult to machine traditionally and even in your standard additive manufacturing machines. So things like the low angles on the internal channels, and like I mentioned before, the risk for your traditional recoder blade interaction on some of the areas that are predicted to warp up, which would make producing this again in your conventional AM machines impossible or difficult, if not impossible. So what Velo is able to do, or what we at least attempt to do, is preserve the designer's original intent. So the exact design that Rashik is able to come up with, keep that as close to original intent as possible. And we do that by using our technology that we call support free, and not necessarily meaning you can print any geometry that you want without requiring any supports. There are areas that do make sense and types of geometries that do make sense, and we're able to print very well without supports, but others that don't necessarily make sense and still do require post-processing and machining and things like that. So with keeping that in mind and trying to preserve that intent and taking advantage of our support-free technology, you got to ask, how are you able to do that? How can you perform those types of operations different than everyone else? And it really comes down to what is kind of I describe as a symphony of tools that we've created. And if we start on the left of the diagram here, it starts with our flow software. So this is our pre-print software where we digest the user's CAD, ideally the native CAD, out of like a SolidWorks package or an NX package, where we're able to preserve all the surfaces that were originally designed in that CAD package. What that allows us to do is be able to select those surfaces, recognize those surfaces, and if we need to, apply special sub-processes or support structures within our pre-print software. The other advantage that it gives us is it cuts out any translational error by having to go through your typical STL type file where you lose a lot of the intelligent geometry that you create originally in your native CAD file. So once we have that build file prepared in our flow software, that is then sliced and creates a print file, which contains all of the laser instructions for the Sapphire printer. That file is then sent over to the printer itself, which is essentially the hardware that creates these geometries that we're trying to make. Our Sapphire system, and go a little bit more detail, is using two 1 kilowatt lasers, following all those print instructions that we've created in our flow software, and has a couple other kind of unique features that allow us to do what we're doing. So number one, we've approached the hardware more from the semiconductor industry, where we want to stay very tightly calibrated, and to be able to do that, we want to calibrate often and make calibration easy. So we've set up a suite of calibrations that are click button type operations, where the operator simply comes up, selects the calibration they want to do, and then walks away and the machine calibrates itself. By having that type of calibration, you can, again, keep your machine calibrated, and we recommend doing it weekly, or if not, before every single build. And then on the back side of that, we put in a ton of metrology where we're monitoring hundreds of data points throughout the entire build to make sure that not only did we set up the machine correctly originally and it's well calibrated, but that it stays within spec and stays well calibrated throughout the entire build. So that's kind of the first two phases of, okay, we've got our file, we've set up our build, we've created all these laser instructions, we've used that build to go, or use that print file to go create this geometry in a well maintained system. And then the last piece is being able to monitor and report out all the data that we are watching and collecting within the Sapphire system. So that gets into our Assure quality software, where we're monitoring things like O2 levels. We're looking at all of our recoats, laser alignment, and things like that throughout the entire build. And we've got a very nice dashboard that gives you a high-level summary of the few data points that we think are most critical to describe tool health, but also has the ability to export all of that data from the entire build and manipulate it in whatever way the customer deems necessary. And bringing all this together is kind of our intelligent fusion process that allows us to really enable support free and maintain as much of that original design intent as possible. So getting more into the printer itself, our Sapphire, and the one we're referring to here, is a 315 millimeter diameter build plate by 400 millimeters tall. It operates two 1 kilowatt lasers, where we are using the full 1 kilowatt capacity to melt our bolt cross sections. list of materials on the next slide, so I won't get into that here, but we're generally running 50 micron layers, running a argon gas environment, and then also have a non-contact recoater, which we'll get into a little bit more later as well. In terms of the rest of our fleet of printers, if you will, our Sapphire family, we have a larger version of the 315 millimeter diameter, referred to as the 1MZ, standing for essentially 1 millimeter tall in the Z direction. It is literally the exact same base printer as the Sapphire with just an extended elevator. And then coming out at the end of this year is our Sapphire XC, so our extra capacity machine with a 600 millimeter diameter plate that's 550 millimeters tall. It's also trying to leverage as much of our original Sapphire hardware as possible. Major difference would be obviously the size, but we're also moving to 8 1 kilowatt lasers instead of 2, but trying to keep those optical trains, the lasers, basic mechanics of the machine as close to as possible of the original Sapphire, so that all the process development that we've done early on with our Sapphire and all the materials that we've qualified are very easily transferred over to the XC. And what we're seeing so far is that, yes, this is indeed the case, and we are fairly easily and quickly able to transfer over parameters to utilize that larger build volume and increase capacity and efficiency of the additional lasers. Some of the materials that we are working with today, 2 common Inconels, the 718 and the 625, a couple of Hastelloys on Hastelloy X and the C22, Ti 6.4, Aluminum F357, and Scalmalloy. In the works, Haynes 282 is actually completed development, and first machine being processed right now to go out to the field with that material. And then soon to follow is GR Cop 42, which is a NASA copper alloy, and a stainless steel CA6NM. Those are kind of our on deck materials, with a few more in the pipeline that are a little bit farther out. Typically, when we're developing a new material, what we've seen in our past is your standard development time is approximately 3 months, depending on how the alloy behaves and how similar it is to some of the other materials we already have developed. Some being greater than 3 months, closer to the 6-month time frame, but some being significantly shorter in a matter of weeks, if they're behaving very similar to something we've already got experience with. Getting back to the design and how we approached it, what we saw, and what we fed back to Rashik and team, initially was brought to us in this orientation, printing the kind of the business end of the bit down towards the plate, which isn't necessarily a bad thing to do. It kind of concentrates the larger sections of the part down towards the plate. But getting back to trying to preserve the design intent, you're ending up having to support a large amount of area on the bottom of that part, and you lose a lot of the complex geometry that is built into the additive component, which would then require you to come back and machine all that in, which essentially eliminates the improvements and capabilities that you're getting by using the additive technology. So understanding the capabilities of our technology, what we can do, and how we're able to support some of these more complex features, we suggested rotating it 180 degrees, printing with the thread end down to the plate, and growing everything else up off of that, which allowed us to kind of maintain, like I mentioned, the design intent of those complex features up at the top, but also eliminate essentially all of the support material, both outside and inside of the part. In terms of capabilities from a generalized standpoint, and what we think of when we are trying to look at your parts and understand what is and what is not possible to do on our printers today, things like dome closures, where we're looking at the ability to build those types of features at diameters of greater than 100 millimeters, and can approach angles at approximately 0 degrees at the top of those closures. Horizontal tubes, so pure horizontal can get maximum internal diameters of 100 millimeters. And really the challenging component of those types of features is that closeout at the very top. But on the small side, we were able to still resolve a 500 micron feature of a horizontal tube. When we modify that tube slightly and give it a small angle and tilt it up, you change the physics of the way that geometry is closing out and becomes more advantageous for the printing process. So we are able to greatly or significantly increase our maximum internal diameter above 100 millimeters, while still maintaining that minimum internal diameter of 500 microns. And then lastly, just horizontal spans, essentially constrained on two sides and unconstrained on the other two, looking at maximum spans of approximately 10 millimeters, and then minimum down to 250 microns. So keeping all these generalized features in mind, we then kind of digest that into the design and what we're able to do in an actual functional component. So here's a good example of essentially what would be like a shrouded impeller with a 3-degree roof. And what you're seeing is the bottom side of the part here that was built and then cut directly off the plate. All the vanes were connected to the plate with the grooves in between the vanes, again, running at that 3-degree kind of from the out to the in, unsupported. So no post-processing or surface finishing has been completed on this part. It was literally just cut off the plate, flipped over, and then the picture is the result of what you can see here. And rough scale of the person holding that in the left side. So really strong ability to be able to print at a high surface quality and generally fairly good surface finish at extremely low angles in these types of features. And then taking the part that Rashik and team provided to us, still doing a couple tweaks to improve or optimize what the printer can and is able to produce. So just moving from top to bottom, trying to remove a lot of the sharp transitions that are in the drill body. Hopefully you can see my cursor, but we had this one that actually dips down negative and then comes back up. So taking a nice smooth blend through there, adding the powder holes like Rashik mentioned, and then utilizing those parameters that we have to maintain that small diameter relative to the large cross section around it so that the powder can still effectively be removed. Doing things like blending these shelves in down here, which in an area that is likely going to be machined anyways, not adding a ton of value by invoking our low angle process. So just adding a little bit of stock there to build as is, supported off of itself. Same with the threads. We have the ability to print threads in, but from a realistic standpoint and a applicable standpoint of using threads in a functional application, you're still going to want to machine those threads to have a good machine surface quality and capable thread. So adding the stock there and having that be machined in after the fact, fairly simple operation, and gives the most capability in that type of feature. And then lastly, fairly simple stock added to the bottom of the part with a fillet to prevent sharp transition and potential for cracking at that initialization point on the build plate. So Rashik also had mentioned some of the stress prediction during printing, and what they had run is for what you can think of as more of your traditional AM system with a fixed blade recoder. So every area in red is predicting a level of deformation and a recoder interaction that would happen on those types of systems. So they've come up with this great geometry, all this functionality, but now are at risk to be able to produce that on a traditional AM system. What Velo is able to do is kind of a two-prong approach. One is take our process parameters and inherently reduce the level of risk or the level of stress that accumulates in those types of features. So bring that overall potential for peeling and distortion down. And then the next thing that we have and are able to do is utilize our non-contact recoder to eliminate the physical interaction at the build plane between a recoder blade and the part geometry itself. To give a little bit more insight in what is happening with that non-contact recoder, you can think of it as kind of a 3-stage process where we move over the build and we drop significantly more powder than what is required for our build layer. And recall, we're building at 50 micron layers, so on the order of a couple millimeters is how much powder we're dropping. Then we come back with a fixed blade and normalize that surface, but still significantly higher than what our final build thickness is. So on the order of 500 microns to a millimeter. And then the last step would be the proprietary removal process, where we're, without contacting the bed, removing the powder, the last bit of powder, to get down to that very precise and final 50 micron layer. So using this process, we have the ability to tolerate geometries that tend to want to peel up and interact with the recoder, or geometries that are very susceptible. Think of things like heat exchanger fins and very thin walls, high aspect ratio geometry that have potential to be damaged or distorted or bent by some sort of physical recoat mechanism that would interact at that level. And then on the inspection side of the recoat, we have this height mapper tool. And what we're doing here is taking 2 types of images. One is like your standard image that you would take every day on your phone, which we take both before and after each layer, and then at the same time doing a structured light scan to create a 2D topological map to understand how the actual powder bed is laid down and what the resulting surface looks like. So by having this scan, we can see if there's any abnormalities or anomalies with the recoat that we've done and how we've spread that powder, if there's some sort of issue and how it was spread. Also, we can see if the geometry is misbehaving at all and protruding out of the bed. So an example here, you'll see the Velo logo. In the left image, everything is great. And the right image, what we're detecting is a protrusion. And what has actually happened here is something below the build layer has become disjointed and powder was flicked up. So the protrusion that is identified, which is well over 500 microns, is actually a clump of powder, not actual lased metal. But by having that structured light scan, we're able to say, okay, there is something above a threshold that we deem safe to continue to build. Have the operator come inspect. They came by, they saw, okay, this is just a clump of powder, do a couple more recoats, smooth it back down, and continue on. With that approach, we can not only protect the printer and the hardware itself, but understand if things are going wrong with the geometry as we're building it, and if something needs to be changed or corrected. So very powerful tool, both in process and after the fact, to help diagnose issues with printer and build. And then what we've got here is just an image of we're scrolling through in the Z direction of our build in our preprint software. So you're seeing as essentially it would be built in the machine, progressing up through the layers. Down in the base here, we've got our build plate stock, and then we grow out into the more complex TPMS internal structures, where we've done not we, but Rashik and team have done the light weighting and added some stiffness to their overall part that grows, and you start to incorporate those complex external features and closing out some of those low angle channels. And then finally, close off the build at the very top. So a couple of things to note in this software on the left is where we've brought in the geometry, again, the native CAD, where we can still recognize all those surfaces. And here's where we have the ability to come select those surfaces and apply any sort of special process that we deem necessary. We can also come in and add support structures. So on the bottom there, the section of geometry shown in blue is a support that's been added in the Flow preprint software, where we've selected the bottom of the part, said extrude this much material down, and add a fillet of radius X to the build plate to make sure we've got good adhesion and we don't crack off of the plate. So very powerful piece of software. And again, it's the initial piece that allows us to progress through this whole complex process. Within that flow software, like I mentioned, we can go put in specialized processes, but in general, we've got a very extensive list of generalized processes that automatically are applied, that Flow is able to recognize based on the feature type, angle, and things like that to the geometry to build successfully. So some of the examples pointed out here, the top facing contours and being able to resolve a lot of those features there, and then also bulk materials. So in some of the thicker sections of the part where we're applying that full 1 kilowatt melted core, we also have different processes for low angles and some of the closeouts on the internal structures. Again, maintaining the small hole diameters for the powder removal and making sure that hole stays clear and as defined in the CAD. And then traditional vertical wall contours and things like that for more of your normal type geometries. All of these types of features are recognized and applied automatically in our Flow preprint software. So then what are we able to do with all that information, and not only print it on a single kind of R&D machine, what we can do with the way we've set up our build files, our software, and our machines by keeping all of this generalized, keeping it all kind of on the same page, having our machines all calibrate the same way and calibrate often, is we can create what we refer to as a golden build file. So create that preprint file, go slice it, develop those print instructions, and then you can then take that build file, put it on any Sapphire printer in anywhere in the world, and you should be able to recreate the exact same results regardless of location or printer serial number, which is extremely powerful thing to do, and traditionally very difficult to do with manual calibrations and offsets for different laser powers and things like that on different machines and different serial numbers, where we've tried to really take a productionized focus on our machine and our technology to be able to do that, so that, you know, if you did need to do some sort of distributed manufacturing, or let's say you don't want to own a machine yourself, but want the ability to go out to our contract manufacturing network and have all of them quote on your part, it only takes one file, one setup, significantly reducing the NRE and giving the customer and the user a much greater ability and flexibility in their supply chain. And what we got here is actually a compilation of the actual height mapper images. So I mentioned we took two types of images. One are regular camera images, which is what we're seeing here, and the other is the 2D topological images. And this is just playing, you stitch all those images through, play them through like a video, and you can see this build progress as if you were sweeping through the CAD itself. And so you get all those different features. You see the complex internal channels, the closeouts, the external contours. A pretty neat way to see this part come together. And then what we end up with is a final print. So the parts shown here on the right, again with the complex internal channels, complex external contours. Quite a good print and good results. And then what's up next for this part is really to do just the final machining, like we mentioned. So cut in a lot of those threads, maybe clean up some of that bottom surface, and then inspect the part and make sure it was produced to the original design intent that Rashik and team had come up with. So I think I'll hand it back to Rashik here.
Yeah, so thank you very much. It was pretty awesome to see all this happening. In these days, the topology optimization, or how can I say, the new softwares coming up, such as Topology, with all the implicit modeling, have created a great opportunity on the design side, that we can explore the design spectrum like never before. But now the issue is there is manufacturing, and Velo3D is right there to able to actually convert that the complex geometries into manufacturable part. So it's a really a good combination of both technologies on design and manufacturing side. We are really moving forward. Some takeaways from this whole project. Of course, we improved weight, we improved the performance in terms of the flow, and we improved the manufacturability of the part itself. The residence time of the fluid which is being extracted is way lower. There is less issues of wearing, and that makes the part the right how can I say, a very really optimized part. And of course, compared to the before, I will let Velo3D answer on the. I saw a few questions regarding the cost, and yeah, I mean, cost has came down dramatically from before. That's something that I can say for sure. And yeah, if some of you guys are coming over to Formnext, I will be there with Velo3D also, who will be presenting there. Don't hesitate to ping me, send me a message, or send any of us a message, and we will try to catch up and answer further questions. Thank you very much. I pass it on to Velo3D.
I'm going to take questions now. We do have a couple questions that came in while the presentation was going on, so we will jump through those. The first question I'll go ahead and take, and that was about will you be getting a copy of this session? So we did record the session. We will be posting it. We'll provide you a direct link to the recording. We do not typically give a PDF copy, but if you want to watch the recording with the speaker actually presenting, you'll get the full story that way. So just a way to kind of preserve the integrity of the content. And so I will ask a couple questions, sort of in the order that they came in. One of the questions, and Sunil, maybe this is for you, is regarding this part. There was a lot of talk about simulation. Was fatigue life taken into account?
Yeah, that was a very good question. And I'm going to answer a couple of related questions from the gentleman who asked this question as well. So we haven't done detailed fatigue life analysis yet on this part, but here are some of the thoughts. First of all, when we were doing the comparative stress analysis from before and after weight reduction type of comparative analysis, we noticed that the stresses in the new design under the loading conditions are fairly small. So that's a good sign as far as the fatigue life itself. Some of the lattice we use something from gyroid class of lattices, and that is typically good for fatigue. That's what people in literature are finding out. We've also added more area and optimized the flow, the coolant flow around the whole part, so that should help keeping the temperatures down. But last but not least, we have to also think about porosity in the part, and those are all the issues that we have to look into this. We've done other parts that are really complex, gyroids similar to this, or even more complex, and where we were able to print them with very minimal porosity or no porosity that would affect the mechanical integrity. So we're hopeful that we'll be able to converge towards a solution, but that's all on the paper. We'll definitely like to take the design to field and see how it compares, right? So those are extremely valid questions, and Rishik's team has great experience in the area of tooling and additive, and this is just an extension of that work. We've got our toes wet in those examples that Rishik has experience with, and this is the next one, which is definitely interesting to a lot of people. Just know that the bits, the idea is not to put the bits as part of the additive. That's going to be impossible. They need to be welded or brazed as a post-processing operation. But the idea is, if you're in the middle of an ocean platform and you need a new bit, can I print one quickly and make it work? And I think we're pretty confident that this type of approach will work. It'll need more validation from some of these interesting questions or interesting issues that you raised. They're definitely going to be important for their life and whatnot. But I think it's got great signs for success in the field.
Yeah, and there was a question here, and it'll probably help to create a little bit of context on where we are with this part. Was this part finished and run on a rig yet? Is the question, and maybe Matt, since you're probably the last one to have seen or touch this part, where are we with this part in terms of its development?
So my understanding, it's been printed, and next up would be to do some inspections, make sure dimensionals are coming in as intended, and yeah, I'll maybe do some of that machining that we mentioned. I'd maybe Rashik or Sunil can give some more color on what happens after that.
We'll definitely be interested in finding partners that can help us test this. I'm sure Rashik has some ideas and partners, but we're looking in that area as well.
Yeah, and we do intend to take this part to FormNext. It will be a printed part, but none of the finishing steps have happened yet. So we want to get this out and give everybody a chance to see it and touch it. But all of the finishing and like what Matt mentioned, the threads like that we printed without any threads. That's a post-processing application. Putting on the teeth would be something that would need to be done in post. So all of that stuff is still to be determined. So kind of stay tuned. There's probably part 2 of this story maybe brewing in the works here. And Rishik, did you want to add anything to that?
Yeah, I mean, definitely. This is doing the experimental analysis on the real part is the end goal of this project. Finding the right partner and right people to work on would be the key right now. But on the same time, not just questioning the drill bit itself, but it's an exploration of what is feasible with the new design technologies and with new manufacturing technologies. And this is just a starting point that where we can expand way more our further design exploration process for other industries also. Not only the oil and gas, but it could be applied to the aerospace, automotive, where we are required to do mechanical CFD analysis and fatigue analysis, and all this should be done keeping in mind that this kind of designs are feasible and manufacturable now.
Yeah. And there was a question regarding the supports, and Matt, this is probably good for you. Were there any internal supports used for the part, or was this part just printed sort of as is from the designer?
Yeah, so the images that were shown is exactly how it was printed. So no internal supports. The only support that was added was down to the base plate. So we had a little bit of a stock to cut through when we were removing it off of the build plate itself.
And there were a couple questions on cost, and I think Rashik, you had an initial comment that this would typically be something like $30,000 to $80,000. And maybe Matt, you could comment a little bit for the printing itself. I mean, would we be north of that or south of that? I know you can't quote an exact number, but to the degree that you can kind of provide some directional guidance.
Yeah, I think in general we'd be significantly less than $30,000, and that's on our Sapphire printer. So keeping in mind that's 2 1 kilowatt lasers operating in unison, things start to get significantly more interesting when we get into our XC printer, where we've now increased our melting capacity essentially 4x by going to the 8 1 kilowatt lasers and having a larger build volume. So you can both print more parts and print parts faster. Which is really interesting and starts to change the dynamic of the economics, if you will, of some of the parts we've been looking at previously and will look at in the future.
All right, awesome. Well, I noticed we are up on time, and I do want to give a little bit of time for closing remarks from our speakers. So Rashik, could you kind of kick us off? Some closing remarks from you, and any final thoughts?
Well, Thank you very much for this opportunity, Velo3D, and I'm sure this is just a starting point where we can find out like what kind of complex structures in various industries could be manufactured. Finding the right application is the key for additive manufacturing, and this is one step further. And hope that we will be doing exploring more and more other industries and other applications together to see how we can bring this whole technology forward as a group.
Awesome. Sunil, same question to you.
Yeah, so I really like what we've done here with Velo and CDS. The last webinar that we did with Velo had a static mixer, and this is a drill head. We're trying to showcase different areas of applications where additive can make difference and show that it's here, meaning it's here as a viable product instead of something that's imaginary and futuristic. We want to hear from you about specific industry concerns for applications around this, so we could show you the capabilities, because we're kind of using this as a canvas to paint with our technologies, combined technologies on, and we would like to see you successful using these things and make your get you your dream product. So all kinds of feedback welcome.
Nice. Matt, final words.
Sure. So I think from our perspective, the kind of the holy grail of additive manufacturing is having designers design parts for function and exactly what they need to do. And our mission at Velo is to enable them to create those components without compromising their designs with support structures or changing geometries or things like that. So seeing kind of that exact approach come to life through this engagement and this drill bit, it really starts to shine the light on what is possible with additive and where we could be going by kind of opening up these design spaces and not having to compromise on the design, so that engineers and designers can truly get their design intent components and applications out in the field.
Nice, thank you. And if we didn't get to your question, or you want to follow on with an engineer, please feel free to reach out directly. Go ahead and do it right now. info@velo3d.com. I'll be able to see that, and I can direct it to the right person, or we can have a conversation offline. Really interested in carrying this forward. Thank you very much. Great job, speakers. Thank you, audience, for joining us today. Fantastic session. Really excited about this one.